Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Synopsys with Namsuk Oh, who's going to talk today about engineering change orders. So, Namsuk, in the past when we had engineering change orders, a lot of those tended to come out of the marketing organization where they saw, oh, this phone has something different than this phone, therefore we need to add it in at the last minute. But now we're dealing with a lot of new markets where almost everything's in flux. What's that done to the engineering change orders?
So actually, when we talk to our customers, there are two themes coming up when they're talking about their challenges when during their ECO cycles. The first one they're talking about is the scenario where corner explosion, where you have to handle so many scenarios. Many customers are handling more than 100 scenarios, and some customers, even we have handling more than 500 scenarios. So when you have that many scenarios, hardware resource, you need to run 500 machines. That is one challenge, but the biggest challenge is that when you actually fix one violation, let's say some violations in one corner, you may end up creating new violation in different corner. So that creates kind of ping pong effect that it's very difficult to converge. So, our customers are asking, is there a better way to do that?
Is it just happening at the most advanced nodes, or is it happening all the way through even at older nodes?
We are seeing that scenario explosion is especially popular when you go to the advanced nodes, but this is not a new problem. This has been there for a long time, especially depending on your design styles. If you have a lot of multi-level voltages or gatings, then even if it is a very old nodes, still you have a lot of corners in the scenarios that you need to take care of. So this is always difficult problems that customers need to solve as well.
Why don't you draw this out for us?
Sure.
Namsuk, what are we looking at?
So here, what we are looking at is 500 scenarios that you need to converge. You need to close the timings. And here, you are going to run static timing analysis, and now you are going to run ECO to close timings. Now, after this, you need to run. You have to get out of this timing tool and go to the new tool, which is going to be implement the ECO, which is going to be place and route tool. So after the implementation, then you need to go to another tool again and extract parasitics. Then after this extraction, then you have to go back to the this static timing tool to restart all this process again until you close your timing. So this is not only the number of scenario is the matter. Now, all these different tools should work very closely to get your TAT reduction. But now the problem here is that because there are different tools, when you are working on one tool should predict the other tool's behavior. Now, but imagine the scenario that I'm gonna draw a layout here. Suppose you have cells on the layouts, and you have empty space that is available for your buffering. Now, ECO tool thinks that, oh, there's an empty space here, so I'm gonna place a buffer. Looks great, and completes ECO and sends this data to the place and route tool. But for whatever reason, maybe user made a mistake or something, ECO tool was not able to see the physical spacing rule that place and route tool sees. Once place and route tool sees this one, oh, I cannot place the buffer here, so I have no option to move that cell all the way up, maybe here. Then ECO router is gonna come and it's gonna create this huge detour, which is gonna create another new violation in different scenarios.
So what you're talking about here is pretty much dependencies, right? So things have to be aware of other things that are going on.
Absolutely, yes. So that is the issue that we want to address with Prime ECO. So basically, we want to integrate all these three engines into one tool so that we can see all the information in one shot, so that the customers can stay in one cockpit and close the timing and ready to sign off their chip. So that's our Prime ECO's goal that we want to achieve.
This gets worse as we move down into, say, 5 nanometers, 3 nanometers, right?
Absolutely, yes.
How about in advanced packaging?
I believe it's the same problem. We need to handle the same problem in advanced packaging as well. But not only just advanced nodes, I mean, all the nodes, this is just common problem that our customers are facing every day.
And you also have more changes in markets like AI and also 5G, for example, because the algorithms and the standards are changing almost regularly, right?
That's a great question. These days, the AI chips are kind of getting very popular. And one of the characteristics of those AI chips are very big. And if it is big, then if you have to run 500 scenarios, it's very difficult to close timing in your schedule. So in that scenario, even it is more important to compress the scenarios, and also reduce your whole this ECO cycle as much as possible.
So, how do you solve this problem?
First, let's suppose we have 500 scenarios. You have 500 scenarios that you need to sign off. Then the prime ECO is gonna analyze all 500 scenarios and group them into two categories. One is live views, and the other one is a static view. Live views are the critical scenarios that you really care. For example, the scenario that you want to measure your frequency of your chip. Then 1 or 2 picosecond is very important. So you want to have the sign of timing accuracy on this live view. Static views are the scenarios that it's not that important, but you have a handful of violations that you must fix to sign off your chip. So those are going to be in the static view. Then what prime ECO is going to do is compress this 500 scenarios into, suppose, let's say 20 live views. Then we are going to keep these 20 live views here, but also we are going to compress these remaining static views into the live views, so that at this point you're going to see exact timing as if you are running 500 scenarios, but with a much less resource available at this point before starting ECO. Now, once you start ECO, 20 live views are, the timings are updated with a sign of timer, but static views are updated with some timing estimation, which is enough to fix all those handful of small violations so that you can close the timing quickly.
Is the goal here to speed up the time to sign off, or is it to have more confidence in the design as it gets to sign off? What are you looking for?
So our goal is to get to the time to the market as soon as possible by providing the tool to reduce this ECO cycles. ECO cycles are usually 50% of the entire design cycles. If you can compress 2x or 3x, you can get to the market much quickly. So it's going to be always customers' wish, and that's what we want to help our customers. So prime ECO, after compressing now scenarios into live, then we are going to put all these engines into one tool, static timing tool, ECO tool, and place and route and extraction tool in one software, so that we can optimize the chip as soon as and as much as possible. Now, if you have all this tool in one software, as you can see, it's obvious that you wouldn't have this very complex multi-tool management, but that is only the small advantage. The biggest advantage is because you have multiple engines are working together, we can be more aggressive and we can close the timing much quickly.
So the challenge isn't necessarily shift left, it's now do more concurrently, right?
Absolutely, yes. That's a great question. For example, if we go back to this example, let me redraw again. Let's say you have a layout here and you have cells and you have the empty space available for the buffer placement. But when ECO tool finds that the space is too small for the buffer that you want to place, in the old schemes, the tool gives up because it cannot find a new place. But with all the tools, all the engines together, now we can move the neighbor cells around so that you can create a room for the new cell. Now the biggest question is which cell to move. There's a point where the legalizer, placer, and the timing tool are talking together. So here in this case, placer is going to ask timer that, can I move this cell? Then it's going to say yes, but this cell is very important. You cannot move. Timing is critical. This cell is okay. This cell is not okay. Then the legalizer is going to move the cells and how much. Then timer is going to tell, okay, you have only 10 picosecond. You can only move this much. This cell has 100 picosecond slack, so you can move a lot longer so that it can create the room without creating new violations. This is where all those tools are in one place and working together, then you can do much more than what you have today.
Do you have more reliability as a result of this because you are looking at all this stuff together?
Absolutely, yes. So if all those engines are working together, you can improve your reliability of your design by creating some reliable placement as a router. And each tool is, because working together, they don't make mistake anymore. They're gonna talk to always the other tool to make the best decision.
Namsuk Oh, thanks for a great explanation.
You're welcome. My pleasure all the time.